Good afternoon, dear students. Welcome to the Chem Tutor. This is Dr. Aino. Today in class, we look at equilibrium constants, and then we also look at coefficients for equilibrium reactions. I understand many of you were unable to grasp the calculations properly, so for such people I've made this very brief video. Okay, so normally when you are looking at calculations relating Kc and Kp, I hope you have not forgotten what Kc is and what Kp is. All right, so equilibrium constant when pressure is involved, that is your Kp. Then equilibrium constant when concentration is involved, that's your Kc. All right, and then so on your screen you can see the relationship. Kp equals to Kc bracket open RT bracket close, then raised to power delta n. So your RT is a gas constant when the value of your pressure is in atmosphere. So that value will be 0.0821. And of course, your T is your temperature. In this case, absolute temperature, because we are dealing with equilibrium. So your N is the number of moles. Okay, change in number of moles. You can see number of mole of your gaseous product and number of mole of your reactants. Ensure that everything you are dealing with are in gaseous state. Right. So I haven't said that in a situation where the total number of mole of your reactant side and product side are the same, your N will be 0. So the equation RT will be raised to power 0. And don't forget, anything raised to power 0 is 1. All right. So having said that, we have an example here. We treated this example in class, but let's look at it again briefly. Okay, let's look at it again. So here you have your equation 1, 2, and 3. You have to consider the equilibrium reaction attained at 823 Kelvin. This is far above absolute zero temperature. So your equation 1 is you have 2 moles of nitrogen monoxide there, then reacting with your bromine gas to give you nitro oxide bromide. All right, so and then you can see your equation 2. Now the Kc of equation 1 is given 2.0, equation 2 is given 2.1 times 10 raised to power 30. Now the challenge is in your equation 3. You are asked to determine the equilibrium constant Kp for equation 3. And what is your equation 3? As you can see it on your screen, you have your N2 reacting with O2 plus Br2 giving you 2 NOBr. So the case, how do you determine your Kc3 for equation 3? Here you can see, like I was telling you in class today, everything that will give you this reactant is very important. All right, and if you look at your equation 1 and 2, none of them make this available. Though you have some of them in equation 1, you have some of them in equation 2. So what do? Look at equation 1. Bromine gas is there, and in your equation 3, bromine gas is there. Equation 2 that will have helped you, all the reactants you need are on the product side. So what do? You invert 1 over. So when you invert, your x becomes 1 over x. Okay, and now you can see, so it means you should also invert the equation. Your product becomes your reactant becomes your product. Okay, you see, so all this comes here, this one comes there, and when you do that, you have your what is written here. I showed you this solution in class. And lest I forget, you can always ask questions in this video, and of course you understand. So you are going to like, you are going to share and all that. All right, let's support one another. We are brothers. So, and subscribe too. Support the Lord's work. God bless you. All right, back to class. So you are free to always ask your questions, and I will always respond. It's a promise. All right. So here you have your equation 2 completely reversed. Without reversing it, you are not going to have the remaining starting materials needed to complete KC3 for equation 3. So after reversing equation 2, you now have 2NO plus Br2, giving you 2NO Br. Alright, you can see it here. Okay, you can see it here. This one. Sorry, this one, N2 plus O2 giving you 2NO. Okay, so your equation is now 1 over, right? So you can see 1 over KC2, right? Now that you have done that, you can now relate your equation 3. Here you have your N2 O2 Br. Don't forget that initially it was only Br2 that was on this reactant side. This side is reactant side, this side is product side. So here you have your N2 and O2. After you have inverted your product, you now have enough resources on your reactant side. All right, so that means you are going to also do the same thing to the Kc values. Kc value for equation 1 remains the same, 2.0, but Kc value for equation 2, which is 2.1 times 10 raised to power 30, is now inverted. That's why you see this one here. This is the same thing as 1 over 2.1 times 10 raised to power 30. All right. So and the logic behind this work is whatever is on the product side can always cancel out what is on the reactant side. Okay. All right. But to simplify it for you, instead of adding and subtracting, you multiply. All right, so your KC3 will be KC1 times 1 over KC2. All right, 1 over KC2. You can see it here. And if you are careful with your calculator, you should get this value for your KC3. All right, so you have gotten your KC part of that equation. Don't forget that your KP equals to your Kc, right, multiplied by your RT here, right, raised to power change in number of moles, right. So I believe this one is clear a little, right. So now with this, there are alternative method. There is an alternative method to do that work, but it's good if you pass through the first route. The first route is simpler, is faster. Okay, it's simpler and it's faster. Now you have your KC3 equals to KC1 and all that. So we have done this. You have done this. Okay. And then you got this. You got this. Okay. So you can now substitute the value you got in Kc, the value you got in Kc, into your formula. Don't forget this is the value you got there. Okay. So you substitute into your formula. And then what do you have? You have your 0.0821 here as your R, that is the gas constant. And then you have the temperature here. Okay. And then you have the Kc you got here. Right. So there is it's not hard. It's not hard at all. Right. Then raised to power 1. This one was giving some people stress in class. So like I told you, your change in number of mole is determined from your balanced equation, right? In your balanced equation, you have on your product side, you have a total number of 2, right? In the case 3, let me show you again. Let me show you again. Let me go back here. So if you look at your balance equation, because a lot of people were worried why we did that. So look at your balance equation. This is 2, then this is 1, this is 1, this is 1 here. Okay, so your delta N is going to be 2 minus 3, product minus reactant. Can you see that? Product minus reactant, and that's going to give you minus 1, right? So that was how we got our minus 1, and you can see it here. You can see, let me clean this board so that you can see. So now you understand how we got this minus 1, right? And it is this minus 1 you are going to put in this your formula here. Okay, put your minus 1 here. Okay, so you can see that. So at least now it's clear to everyone how you got your minus 1 as the value for change in N. And when you carefully substitute all this value into your formula, you're going to get 1.41 times 10 raised to the power minus 32. So you can see it's a very interesting reaction. Let me stop here for now. Expect more interesting videos, and just to get you understand everything we need. Right? Don't forget, you subscribe, like, share. God bless you.